I'm going to skip answering homework questions today, but I'll do it on Friday, just so we can try to get to a point where you can work on some more problems. So last time we finished talking about the mathematical stuff that we need. And now we're going on to the first kind of dynamics topic. So our new topic, our first topic, is particle kinematics in non-rotating coordinate systems. And later on, one of the last topics that we're going to do is going to deal with rotating coordinate systems. Dang it.
Kinematics, that's pertaining to accelerations and velocities. That's just like the formal name for that.
Yeah, that's right. So I was just going to go through all the meanings of these things. So, but yes, you're exactly right. So kinematics you can think of that as describing motion without dealing with the causes. And the causes would be like force, mass, and energy. So kinematics is all stuff you could do from a videotape of something. You know, if you had measurements all out in your room and you could time things from the video and see how far they went, you could do these calculations. From a video, you can't tell how much mass something has or how much force is being applied. So we're not dealing with those. But this is relationships between time, position, velocity, and acceleration. And you can have kinematics of rigid bodies. You can have kinematics of deformable bodies. This is kinematics of particles. And the meaning of particles is you tend to think, most people tend to think of particles as small. That's not necessarily the case. A particle is just something that so it's a mathematical treatment of an object. As existing at the center of mass and having no length dimensions. So it's the size of a point, you know, it has no size at all, and it's just moving around, and it represents the center of mass of the object. And this is kinematics, so we're not dealing with mass yet, but a particle does have mass. It just doesn't have size. using Newton's laws, which is what we're going to do here, you can treat anything as a particle. If you don't care about the object's orientation. You can't do that using an energy approach. So you have to be careful when using an energy approach. But we're not going to do that yet. But the reason is that when you're using an energy approach, basically you think of potential energy and kinetic energy going back and forth. Well, bodies have translational kinetic energy, but they also have rotational kinetic energy. And potential energy can be exchanged with rotational kinetic energy too. So, and a particle doesn't have rotational kinetic energy. So if you try to so like for example, if you have something rolling down a hill and you plan on treating that thing as a particle, it starts with potential energy. A lot of that potential energy goes to making it rotate. And so you'd be wrong about the speed that you have at a certain point. But using Newton's laws, you can treat anything as a particle if you don't care about orientation and moments and stuff. Okay, and then non-rotating coordinate systems. So that's important. You've never dealt with rotating coordinate systems before, but we will later in this class. And we're going to do sort of 4 sections in this topic, under this heading. The first one is the time derivative relationships. So acceleration, the acceleration vector is the time derivative of the velocity vector. That other one's open, I think, right? They'll make it. Yeah, if they're smart. Okay, so we have those time derivative relationships. And we've already talked about how to take time derivatives of vectors in non-rotating coordinate systems, so we know how to deal with that. The second section is the chain rule. And we're going to use the chain rule when we can express the velocity vector as a function of the position. This comes up probably most naturally if if you're using an energy approach to come up with speed as a function of position, okay, then you can often come up with the velocity vector as a function of position. Well, you don't have it explicitly as a function of time, but you can use the chain rule to get through it, and we'll talk about that. And then the third thing is circular and spherical motion. So that's something moving a constant distance from some center, okay, a constant radius around some center. And in 2D, that would be a circular motion. In 3D, that would be a spherical motion. And then the last one is relative motion. We'll see that this works really naturally with circular and spherical motion. And these two together are very useful for linkages, which is collections of rigid bodies connected by joints. Okay, so the first one is the derivative relationships that says the acceleration is the time derivative of the velocity, is the time derivative of the position, or acceleration is the second time derivative of position. So the one main thing that you have to understand about this is that you don't want to think for example, velocity is the derivative of the position. It has to be a time derivative. And so if you have the well, and same thing with acceleration. Don't think of acceleration as the derivative of velocity. So like, for example, if you have the velocity given as a function of x, you can't just take the derivative with respect to x and think that that's the acceleration. You can only take the derivative with respect to time to get the acceleration. Okay, there's two directions you can go with these derivative relationships. The first one is you can go in the direction from position to velocity, or velocity to acceleration. In that case, having a function of time is enough. All you have to do is take the time derivative. So, for each step, you're just taking the time derivative. So like, for example, if the position vector is t squared, then that means that the velocity vector is just the time derivatives of those components. So it's 1, 2t. And that's velocity as a function of time. And that's clear that that position is a function of time, that velocity is a function of time. If you want to know the velocity at a specific instant, just plug in the time that you care about, and it'll give you the vector. And then the acceleration as a function of time is 0 for x, 2 for y. Also go the other direction. So where you're going from acceleration to velocity or velocity to position. In that case, having functions of time is not enough. Because in this direction, you're solving a differential equation using separation of variables. So each step, going A to V or V to P, is a separation of variables problem. And that means you need one boundary condition for each component. So for example, let's say that you know that velocity as a function of time is equal to t squared cosine t. What's the position as a function of time? Well, just intuitively, this is telling you how fast something's moving and in what direction, okay? But it could be happening right along the ground, or it could be happening 30,000 feet up in the air. Obviously, that information is important to come up with a position function. So that's what you need for the boundary conditions, okay? And so since we're thinking of things at least in 2 dimensions, it could be way up in the air, or it could be down close to the ground, or it could be here, or it could be, somewhere in Russia or whatever, So you need the boundary condition information to say where that position is starting. So the boundary conditions would be given something like this. So say that we're given that the position vector at time equals 0 is equal to 0, 50.
When you say one boundary condition for each component, you mean the x and the y?
Yeah, that's right. Okay, so at that point, you can say, so you can think of that velocity vector as an x and a y component. And we know that dx dt, that's the x component of the velocity. is equal to t squared. And so dx is equal to t squared dt. And now we can integrate both sides. And we get that x is equal to t cubed over 3 plus c. And now we use the boundary condition. The boundary condition says when time is equal to 0, x is equal to 0. So x is equal to 0 when time is equal to 0. And that lets us calculate that c is equal to 0. And so from that, we know that the x position as a function of time is just t cubed over 3. And now we go to y. This is, so when you're doing this with vectors, what you're doing is an uncoupled system of ordinary differential equations. Okay. The x stuff stays in the x equation and the y stuff stays in the y equation. So you can just do them as separate, two separate differential equations, or three separate ones if it's in 3D. Okay, so now the y equation says dy dt is equal to cosine of t. So dy dt, which is just another way of writing the y component of the velocity, is equal to cosine of t. So dy is equal to cosine of t dt. And you can integrate both of those. And you get that y is equal to sine of t plus some other c, I'll call it c2. And now use the boundary condition to find c2. The boundary condition for y says when time is equal to 0, y is equal to 50. So plug that into this equation and we get 50 is equal to sine of 0 plus c2. Sine of 0 is 0. So c2 is 50. And so y as a function of time is sine of t plus 50. And so then put these two together, the position vector as a function of time is x component, t cubed over 3, y component, sine of t plus 50. And so now plug in any value of time and it'll give you the position vector, which the position vector you can also just think of as the coordinates of the object at that instant. Any questions about that? Okay, the next section in this topic is calculating the acceleration vector using the chain rule, when you have the velocity vector as a function of position. Okay, well, I'm going to just show this with two examples. So first, let's say that we have a velocity vector that's given as a function of x. So it's given as a function of the horizontal position component. And let's say that it's equal to x 5x. Okay. And we want to know what's the acceleration vector as a function of x. Well, the thing you don't want to do is just think that acceleration is the derivative of velocity, so you just take the derivative with respect to x. That only works if the independent variable is time. Okay, but what you can do is recognize that using the chain rule, the acceleration, well, the definition of the acceleration is the derivative of the velocity with respect to time. Okay, but the chain rule says that that's equal to the derivative of the velocity with respect to x times dx dt. Dx dt is the x component of the velocity. And so this is equal to dv dx times vx. And so in this case, the acceleration vector is equal to 1, 5, that's dv dx, times the x component of the velocity, which is x. And so you get x 5x for the acceleration. Well, I guess because it was linear, it comes out, just by coincidence, it comes out to be the same function as the velocity vector. But this is the acceleration as a function of x. Let me do an example where the independent variable is y. So let's say that you have velocity as a function of y is equal to negative 10y and then negative y squared. Well, the acceleration is dv dt, and dv dt by the chain rule is dv dy times dy dt. And dy dt is the y component of the velocity. So this is dv dy times vy. You do the calculation using the functions that were given here. Dv dy is -10, -2y. And then the y component of the velocity is -y². And so that comes out to be 10y² 2y cubed. Any questions about that? Okay. Well, what's a case where this would happen, where you'd start with the velocity as a function of position? It's actually more likely. Yes. Yeah. So if the velocity was given as a function of the components of the position. Okay, don't write this down. Let me think about this for a second. So if you had like the velocity given as a function of x and y, so that would be partial of v with respect to x times dx dt plus partial of v with respect to y times dy dt. You could do it the same way, but we're not going to deal with that. Okay, so you'd have to use partial derivatives and stuff, but we'll just not do that. Maybe next year I'll make people do that. Okay. Yep, and it works just the same way. Yep, that's right. So the only thing you have to worry about is which of the three position variables it's a function of, and then be sure you take that component of the velocity to multiply it by. Okay, so what's a case where, so this is pretty unlikely. There's a problem or two that I have you do where you start with velocity as a function of position. But what's more likely is that you're given an object's path because it's moving around some fixed path, uh, something swinging around a string, the path it's on, it can't go outside of that circular path. Something moving along a wire or something, that's a fixed path. And then in addition to the path that it's moving along, you're given speed as a function of position. And that would most likely come from an energy calculation. Uh, like when you did simple conservation of energy problems in physics 1, like someone skiing down a hill, um, you could, the position variable was the height on the hill, and you could use conservation of energy to calculate what the speed was at that instant. Okay. And then you need to determine the velocity vector as a function of position from that. And then use the chain rule. So let's say that, let's see, do I have a good example of that?
So you're saying there's not a case where you would velocity vector position?
You have to get there before you can use that chain rule, but more likely, like if you come up with a problem like this from a real situation, instead of directly getting the velocity vector as a function of position, you'd be given the path that the object's moving along, and speed is a function of position. And so to do that, you need to remember that velocity is equal to the speed times a unit vector in the direction of the object's path Okay, so the speed would be given. The harder thing to get is the unit vector. So to find this unit vector, given a path that would usually be given as y equals f of x. Well, a parametrization of this, it's called a parametrization. Let's just call it. So the position vector then is x f of x the derivative with respect to x gives you a vector. So the position vector derivative with respect to x gives a vector tangent to the path in the direction of increasing x. So now a vector that's in the direction of the motion, we can call the vector u. It's not a unit vector yet, but that's equal to 1 f prime of x, and it can be plus or minus depending on whether the object's moving in the direction of increasing or decreasing x. And then you just have to take a unit vector in this direction. So the unit vector is 1 over the magnitude of u times u. Okay, so let me do an example. That's pretty abstract. Okay, so let's say that an object moves from right to left along the path y equals cosine of x. Okay, and let's say it has a constant speed of 5 meters per second. What's the acceleration vector as a function of x? So there's the path, and the object is going from right to left. And we want to know at each one of these locations, what's the acceleration of the object? It's not changing speed, but it is turning, so there's going to be an acceleration related to that. Okay, well, we know that the velocity vector as a function of x is equal to the speed times the unit vector. And the speed is 5, so that part's easy. We just have to come up with a unit vector in the direction of the path. Well, a position vector is equal to x cosine of x. And that means that a vector that's tangent to that path, I'll call it u, is equal to the derivative of both of these two components with respect to x. So that's 1 negative sine. And the direction the object is moving is from right to left. So that's in the direction of decreasing x. So we're going to take the negative here. And so we have negative 1 positive sine of x. And now we need a unit vector in that direction. The magnitude of u at any given x value is 1 squared plus sine squared of x square root. And now divide each of the components of u by this, and that gives the unit vector. So the unit vector is equal to -1 over this square root positive sine x over this square root. And now we have it. Just multiply this unit vector times the speed of 5, and you get that the velocity as a function of x is equal to the speed times the unit vector, which is -5 over that square root. Five sine x over the square root. Are we done? No, that just got us back to the point that we started the last problem on. Okay, but now you use the chain rule, and I don't have time to do this. It's obviously a pretty messy derivative, but you can see we can do it now. The acceleration as a function of x is dv dx dx dt. So dv dx times the x component of the velocity. Yes?
I'm a little confused.
Mhm.
When you say in the direction of the component,
Okay, so yeah, so at every point, so let's think about the particle right there, okay? We're trying to come up with a unit vector in the direction of its motion at that point. The direction of its motion is always tangent to the path. And so it's moving from right to left. And so the tangent to the path at that instant, moving from right to left, is that green arrow.
okay, but that is not an x direction. So
Well,
to the x direction. I'm just trying to.
okay, so the direction of increasing x or decreasing x just tells you which way you're going along this path. So if you're going along this path this way, the x values are steadily increasing.
You just mean tangent to that function.
Yeah, but you have to remember that there are two tangent vectors at that point. One is this way, and one is the opposite of that.
So you're talking about what's going in the direction. In this case,
right.
Negative would be going.
Right. Yep. So you have to remember to figure out whether to multiply it by +1 or -1 to determine whether it's going. So if it's going in the direction of increasing x values, which would be left to right, then you don't need to multiply by -1, and you get a vector going that way. Multiply by -1, and you get the opposite of it. Okay, I know it's confusing for everybody, but that's what it is. And it's sort of a just painful reality that those derivatives end up being really messy. It's pretty hard to come up with examples where they don't get really messy. But it's also, I mean, if you think about what that's able to calculate, you don't have any way to do that otherwise. We started with just knowing that this was moving at a constant speed along this complex path, And we came up with an expression that lets us know the acceleration vector at every point, which then you could use in Newton's laws and whatever. Yeah. Yeah, is it scheduled? Okay, yes, thank you. Quiz Friday. I mean, I knew it, but thanks for remembering yourself too.